So the common ratio part is 2/1, 2, 4/2. You get 2, 8/4, 2, 16/8, 2. Hence, geometry, we have a common ratio. If I start the series right there, every single term in the series can be written in terms of the first term. Do you agree? Yes. So what do I mean by that? Well, I could write 2 squared, 2 cubed, 2 raised 4, 2 raised 5, ... Yes. Well, if I call that to be A, I can write that as A times 2. Agreed. I can write that term as A times 2 squared. Yes. The next term would be A times 2 cubed. A times 2 raised 4, ... Yes. And if I pull A out, I would end up having 1 2 raised 2 written as 2A, so I'll have 2 followed by 2 squared, 2 cubed, 2 raised 4, ... Agreed. Well, what is the common ratio? We already established that. The one on the top, sequence on the top, the one that diverges. 2. So I can write this as R squared, R cubed, R raised 4, ... It looks like the first one is the troublemaker. Agreed. It is not giving me 1. Or it seems like it doesn't follow the pattern. What should I do? Start at 0. Yes.
Oh, I was just gonna say you could make it. You could make the term 2 to the 0. That would be the same thing.
So I can write it as A raised 0, or R raised 0 times A. So the sequence that I wrote yesterday pretty much is geometric, where the first term A is just 1. Yes. If you look at this right here, it is nothing but that right there. Agreed. So that's what I mean by starting at 0, starting at 1. You can start at 2. It varies. But if I start at 0, the sequence will be A, 2A, 2A, 4A, 8A. In terms of R, it would be A, AR, AR squared, AR cubed, ... AR, pivot N minus 1. If I start at 0, because the general term is what we are going to use in our series, so we better get this right. So my question to you is the power there, n or n minus 1. The general term must generate the sequence. And we've already established n is going from 0, 1, 2, minus 1. What should go right over there? Is it n? Is it n minus 1? That is important because that will define our sequence. That is what's going to go in our series. So we've got to know what that number right there is. If I say things start at 0. Caleb says n. Do we agree with him? James not agreeing with you.
Because when we defined the series as when the starting term was 1, it's AR to the n. So naturally, if we go back one term, it would have to be n minus 1, right?
I'm starting at 0.
Yeah, but all the other ones were defined at starting at 1. If we're going back one term, wouldn't we have to do n minus 1?
If I start at 1, sure, it has to be n minus 1. And I'm starting at 0.
Oh,
Right? So this has to be n because n equals 0 would give me that term, n equals 1 would give me that term, n equals 2, that term, n equals 3, that term, 4, that term. Good? Yes? But if I insisted and I said, instead, we start at n equals 1, 2, 3, ... Then when n is 1, I need to get a. I can't change the series. The series has to remain the same. So a, ar, ar squared, ar cubed, ... general term, comma, ... I would like to know what goes in that box. If our matter means that n has to start at 1.
so in this case, it would be n minus 1.
Very good. In this case, it would be a r raised n minus 1. The general term must generate the sequence properly. So if I insist that n must start at 1, the general term would be r raised n minus 1. Good. Now that is a geometric sequence. Depending on the value of r, the series would either converge or will diverge. And what is a convergent series, or excuse me, sequence?
It goes to 0.
What goes to 0, Megan? The numbers in the sequence eventually dissipate and become 0. Instead of going to 0, it just blows up, then it's diverging. So there are 2 cases that I started with. I started with 1. It might seem that it doesn't fit the pattern, but it does, because if I pull the first term up, that and that, they match up, right? That's it. Look at the one on top and one bottom, the 2 sequences. Diverges, converges. What do you see in terms of R? In other words, what does R look like? What is the difference between the sequence here and the sequence there in terms of R? What can you say about R? That's what I'm asking. Is R 0? Let's start there. Clearly not. It's obvious, right? R is 0, we're not going anywhere. So
R is 1.
R is 1. Why? 2/1 is 2, 4/2 is 2, 8/4, 2, 16.
1/2. The one.
Okay, so how is that special?
I don't know.
You don't know? But close.
Just be 1/r.
1/r, okay.
1/r to the new.
1/r raised 10, okay. It's one way of looking at it.
Never mind.
There is something else in terms of those two. Let me write one more and let's see if we can see the pattern. Perhaps. So, two sequences. Good. One more. Give me a number between 2 and 10. Unequal 4, okay. So 4 squared, cube, or a 4, or a 5. Want you to look at that. Diverges. Converges. What do you see in common? There is a pattern, JT.
So if one series diverges, the reciprocal of the common ratio converges.
Okay, that is true, but the answer is simpler than that.
What specifically are you asking?
There is something interesting about, or there is a limitation. Let me put it that way. What is that limitation? You look at the R here and look at the R's that you see there. 0.
Yeah, because the one that converges just go lower than 0.
True. It is going to converge to 0 eventually. But there is something interesting about these numbers in contrast to those. I'll give you one more.
Fractions.
Thank you. Those are fractions, right? By all means, they are proper fractions. Agreed? If you have a proper fraction, the value will always be between 0 and 1. Do we agree? That is what a proper fraction is by definition. If a number is between 0 and 1, the denominator is always bigger than the numerator. So if you keep on increasing the power, that fraction will eventually become 0. Yes? These are integers. You may say, well, why not why can't I write it as a fraction? Well, you could write it as an improper fraction. For example, you could write it as 5/3, right? 5/3 is 1.67, right? So you start increasing the power of 1.67. Let's say you start with 1.67, 1.67 squared, 1.67 cubed. I want you to try 1.67 raised 25. You have the calculator, tell me what you get. Okay, so Caleb tells me 1.67, raised 25, it's roughly 37,000. Give me a number,
307, my bad.
370, okay, 37,000 seemed a bit low. Give me a number between 80 and 150.
370,000.
370,000? Okay, 300, some big number. Give me a number between 80 and
112.
Huh?
You said 112.
112. That's what we're going to go with?
Yeah.
Okay, do 1.67, raise 112. What do we get?
8.8 times 10 to the 24.
8.8 times 10 raised 24. Okay, give me a number between 200 and 250.
223.
He said 249. So 1.67 raised 249.
9 times 10 to the 57.
2.9 times 10 raised 55. What is happening? Keeps on going up. Okay. Now let's take that one away and keep it as 0.67. Good. Repeat the same. We started with 25, 0.67 raised 25. What do you get?
Four point five times 10 raised to -5.
4.5 times 10 raised -5. A small number, not that small, but small. How about 0.67 raised 112?
Point 3 times 10 raised to -20.
3.3 times 10 raised -20. One more. 0.67 raised 249. You should get the point by now, right?
Getting closer and closer to zero.
It's getting closer and closer to zero. So the characteristic that you see in the common ratio number sequences, the one in the bottom, in all three cases, they are proper fractions. So they are integers, could be an improper fraction. So that is going to give us our condition for a convergent geometric series or a sequence. Good. It has to be 0 to 1. It cannot equal 0 because if the ratio is 0, you're not going anywhere, right? It's just a sequence of zeros. It cannot equal 1 because it's not converging. Good. So what if I did -1 to 0, excuse me. In other words, R is a proper fraction, but it's only on the negative side. So will that converge? Give me a negative proper fraction. Okay, I heard -1/3, -1/2. We're going to go with -1/3. So if R is -1/3 and say, let's start at a raise A times R raised n equals 0. So I will have 1/3. With the negative. 1/3. Squared. Good. 1/3 cubed. 1/3 raised 4. 1/3 negative 1/3 raised 5. Negative 1/3 raised 6. I'm sure you'll get the point by then. Good. Yes, no, maybe. So I would have negative 1/3, 1/9, negative 1/27, 1/81, negative 1/243, positive 1/9, 729, dot, dot, dot. Right? What difference do you see between, say, this one and that one?
Well, there's negatives and positives.
Negative and positive, it's going back and forth, right? So this is an alternating geometric series. It goes back and forth, yes.
So that's if, R is 0, -1 to 0.
Come again? Yes, that is correct. So I didn't mean to say series, I meant to say sequence. So in this case, the fraction that I have is proper. It is between -1 and 0. Not inclusive. Now here is the question. Do you think that alternating series converges? Diverges? Why, Caleb?
It doesn't approach anything.
Doesn't approach anything. Do we agree with Caleb? So Caleb says alternating, so it is not going to approach anything, so it's a divergent series. Do we agree with Caleb? Michael number 2 disagrees with you, Caleb. Why?
Because even if it's negative or positive, it's still it's closer to 0.
Exactly. Whether it is negative or positive, eventually it will get smaller and smaller. Yes. Instead of taking a pattern while the sequence goes like that, approaching 0. It is going to follow that pattern. See the difference between the two?
So then would it look like a wave if you were?
It's going to look like something damped.
So it looks like a wave.
Yep.
And that means it crosses 0 at some point.
Yes.
So would that mean that it?
Oh, sorry. As a sequence, I see what you're saying. Let me explain this. If it is a function, then sure, when it crosses, it would become 0. But this is not a function, it is a sequence. So I'm saying it's going to take this value, then it will take that value,
Got it.
then this.
So there's no
Not-
space in between, it's just point.
Yep. So it's going to go back and forth. I am not connecting it by a line, because it's not a function, it's a sequence. Good? But it does converge. Alternating geometric sequence converges, geometric sequence converges. It happens so in this case because R is between -1 and 0, not inclusive. Yes.
So what specifically is the difference between a sequence and a series?
When we did series last time, what did I start with? Very beginning, I started with something. And I said, well, I write this with the natural numbers, then I write this, then I write this. And eventually I said, this is too much to write. The sum, right? So that summation notation is what we call a series. There is more to this, but for now, take it as is. That summation notation is what we refer to as a series. But you can't do a series without understanding the sequence. Good. Okay. Cannot erase this. So the convergent or divergent geometric series could either be alternating or not alternating, but it all depends on the value of R. R has to be between -1 and 1. Last time when we were talking about series, a related series and sequence, and I said if you have a sequence that diverges, then the corresponding series will also. I really said also, so there's only one answer.
What'd you say? You said converge. Oh, converge.
Converges, what?
I was just repeating what I heard.
If a sequence diverges.
Oh, then that.
Okay, I used the word also. So the series would also diverge. So what do I mean by that? Well, let's write the partial sum for a sequence, geometric sequence A R squared, AR cubed, ... It doesn't matter as to what the general term is or where you start. In other words, you could have k equals 0 up to n-1, A times R. When you start at 0, what was there in the power for R? The general term, and you start at 0. N. So in this case, it would be k, because the index is k. Good. Zero. I'm going to pick, oops, sorry, 1. I'll go all the way up to n, A, R. What should go up there?
K minus 1.
K minus 1. This series, that series represent the same summation. Good. Both this general term, that general term, they generate the same sequence. They just are indexed differently. With me? This one starts at 0, that one starts at 1. If I counted 0 through 9, how many numbers do I have? 10. If I counted 1 through 10, how many numbers do I have?
10.
10. Why 9, Caleb? Oh, who's Tito?
You said that.
So either way, you get n terms, right? N. Okay, but this is not a sequence, this is a series. I'm summing the first n terms of the sequence, yes? So it is the nth partial sum. This is a finite geometric series, and I am going to say that R is between -1 and 1. There is also another way to write it, if you look in Wikipedia, Google, YouTube, whatever. This is nothing but the absolute value of is less than 1. It cannot equal 1, good? And it cannot equal 0. It's important. Good. Okay. As an example, give me a proper fraction between 0 and 1.
1/16.
1/16. Okay. That's a huge number. 60, that's bigger than that.
Want the answer?
Yeah, sure.
65,566.
65,506. I was going to the next number for some reason. Oh, it's 216. 217. Okay. So, 16, 256, 8,192, 65,536. This is going to converge. Do we agree? Yes? Okay. Let's say we want to find S1. What is S1? Doesn't matter whether you use this or that. The answer will be the same. Right? One term. So the end partial sum, the S1 would mean you're just moving one step. What is that answer? You're summing the first term. You started the first term, ended the first term. What is the answer? 116. 116. Okay. What is S2? What? 1/256
Plus 1/16.
plus 116. Seventeen over 256. S3 is 1/16 plus 1/256 plus 1/8,192. Can I erase this over here? Yes. All right. There. S3 would be equal to 16 cubed. 33 over 8,192. Did I do that right? Come on, people. 16 here. Okay. I can keep on going. I'm going to stop there. So do we see the partial sums? Do we see the series converging also? We started at 1/16. 1/16 became 17 over 256, which became 33 over 8,192. Is it getting smaller? Hayden? Yes. So naturally, I have a convergent geometric series of sequence, so the series is going to converge. Now, do I want to sit and write this out? Is there a formula? One thing to note, anytime we have, series, there is a possibility for what we call a recursion. Recursion in the sense you can write one step in terms of the previous steps. So I can write Fn as Sn minus 1. Yes? Taken. Right, so I can write Fn as Sn minus 1. So in this case, S2 can be written in terms of S1, which is right here, plus the next term. How did we get that next term? By adding the second term. In other words, 2, yes? So I could say, instead of calling it 2, R raised n. Yes, S3 would be equal to S2, whatever sum you had, and you are adding 1 over 16 raised 3, which is 1 over 8,192. That's pretty much what I did. Agree? If you move with this process, theoretical math, eventually you can't find an expression, find an expression for a finite sum of a geometric series. You have a formula, A times 1 minus R raised n over 1 minus R. Provided the series is defined by or defined in that manner, that sequence. Okay. You can plug it in our formula and see if it works. Hopefully it does. If I plug in 1 minus R over 1 minus R, they will get cancelled. You get the first term, yes? If I plug in 2, side note, 1 minus 1 over 16 squared over 1 minus 1 over 16 times 1 over 16. I'm just plugging R in the formula. So 1 over 16 times 16 minus 1. 1 minus 1 over 256 divided by 15 over 16. Agree? Okay, what else can we do? Flip and multiply? Masking. Denominator fraction, if you take it and multiply, you'll get 16 over 15. Those two will go away. Perhaps I'll use a different color. So 1 over 15 times 256 minus 1 divided by 256. Yes? 256 minus 1, 255. One over 15. And what is that? I should come to 17 over 256. Don't it? So if you simplify. Now, you can verify this. If you use this recursion, if you keep on going, you can show that the sum will be that. So that is the nth partial sum formula for a geometric series, provided the sequence, geometric sequence in that series converges. Are we clear? Yes?
So it only works if it converges.
Now you could find a sum, but even before you get to a few terms, the series would start blowing up because you're adding really, really big numbers over and over. So it has to converge. Good. Okay. Well, we know it converges. I want my bank account to be or to have a geometric sequence starting today with a common ratio of 2. So that over time it would accumulate and my bank account would become a geometric series with a common ratio of 2. And I'm going to wait 1,000 days from today. Do you think I can use that money and leave this galaxy? Or at least try?
No.
I can try. I think that'll be lots more money than Jeff Bezos or what's that other guy's name?
Elon Musk,
No,
Elon Musk.
screw it. No.
Zuckerberg, he's the richest.
No, Richard,
Nixon.
it'll come to me. Wow. The guy who, it'll come to me. But I want it to be divergent. The sum is going to get bigger and bigger and bigger. It's going to blow up. I'd end up having a lot of money. But if things are shrinking beyond a certain point, Richie?
You're thinking Warren Buffett.
No, I'm not thinking of Warren Buffett. Richardson, he's an English guy. He owns Virgin Atlantic.
Prior.
No, Richard Pryor.
Currently owning it?
Huh?
Does he currently own it?
I think so. It's okay, not important, let's focus here. Eventually, if the sequence approaches 0, do you think my bank account will grow? No, but if I don't take anything out at all, would it flatline at a certain amount? After a certain point in time, let's say instead of 2, it is 1/2. Whatever amount I have, it's getting halved over time. And 1,000 days go by. I'm not looking at the sequence, I'm looking at a series. So what will I have? If I don't take any money out, would I have a fixed amount at the end of 1,000 days? Caitlin says no. How about this, Caitlin? I started 1/2, 50 cents. 30 cents becomes a quarter. Adding together, I get 3/4. Yes. 1/16, adding to 3/4 plus something, correct? So I keep on increasing this amount. But eventually, there will be nothing for me to add. Agreed. But things would have flat lines because I'm not withdrawing anything. Now I'll be broke, but it's a flat amount. So that is what we call an infinite sum. What is an infinite sum? Well, we have a nice little formula for that. Can I erase it? If you have a convergent series, you can find its infinite sum. Sometimes there are, get it, sometimes No one got it, moving. She's the only person who gets my joke. Infinite sum is possible for some series. One of those series is geometric. Last time that I wrote a series notation, I said if you want to find an infinite sum, assuming the sequence is convergent, we simply do limit n approaches infinity, correct? So Sn, which would be limit n approaches infinity, a times 1 minus r raised n over 1 minus r. Let's see if we remember calculus 1. A is a constant, 1 minus r is a constant. Can I pull those out as the limit? Yes. So A can come out, 1 minus r can come out. Okay. Does the limit affect the number 1?
Yes,
How?
it makes it very small.
Do you see n here?
No.
Do you see anything? No, so no n, so this is not going to be touched. So 1 minus r times 1. What about the second term? Minus limit n approaches infinity, r raised n. Assuming a convergent geometric sequence in the sense the absolute value of r is between -1 and 1, and r is not equal to 0. We just saw what happened. We used 1.67, then we used 0.67. What happened when we used 0.67?
Approach 0.
It approached 0, okay. So if r is a proper fraction and not equal to 0, of course, will that term become 0 as n approaches infinity? Yes, that will go away. Left with just that. So as infinity good. So back to my bank example. I'm going to start with 50 cents. Depositing 50 cents while I'm listening to 50 cents. R is 1/2. Good. The first term is 1/2. Because I'm starting with 1/2, 1/2 becomes 1/2 squared, 1/2 cubed, yes. So a r raised 0, a r raised 1, a r raised 2. Good. Yes, no, maybe. Okay. A is 1/2. Good. Well, if I wait the rest of my life, I'll have 1/2 divided by 1 minus 1/2, which is -1/2, -1/2,
-1/2.
1/2. So those two will get cancelled. 1. So if I deposited 50 cents today, and it grew geometrically as a geometric sequence, and I waited for all eternity, I would have a dollar. Does that make sense? Yes, okay. Not every series would converge. There are series that simply won't. And then we've got series that alternate. And I erase this one. So the geometric series case that we had, should be start at 1 or 0? Let's start at 0. Well, we can make it infinite. Minus, well, r raised n. Now, the formal term, geometric series or any series usually will refer to an infinite sum. So when we write an infinite notation, we'll call it a series always. In other cases, we'll just call it a partial sum because you can sum up to partial terms, but regardless, you get the point. So this would be A. If I know that R is a negative number, so let's say R is negative I don't want to use A, B, C, D. How about S? Some number where S is bigger than 0. Oops. S is between 0 and 1. In other words, S is the proper fraction. I got a negative number. A times the R raised n part, I can write it as negative S raised n. Good. Which I can write it as, first I'm going to pull A out, so A, or didn't mean to write N, my bad, it's K, the index is K. From 0 to infinity, infinite series, minus 1 times S raised K, with me? Good. And that would equal to sum K equals 0 to infinity minus 1 raised K times S raised K. Good. The reason why I'm writing this is because this is an alternating series. Do we agree? Most common mistake that students would make is writing negative 1 raised K as negative 1. You cannot. Just like a limit. When you evaluate a limit with respect to x and you've got a bunch of x terms, you can't get rid of those x terms because the limit will act on those terms. So the summation index right here is k, and I have k up there. So you can't bring that out. You can't simply write it as negative 1. By all means, what would make the series or the sequence in the series alternate is that term. So anytime you have a general term with -1 raised k, then you would have an alternating series. Good. Some alternating series will converge. Our geometric series is a great example. Michael number 2 said, well, even if it is a geometric series with alternating signs, eventually it is going to become 0 as long as the conditions are satisfied. Yes? But there are alternating series that simply will not converge. Again, geometric series are greater than 1 or just are equal to 1. So here is a geometric series with r equal to 1. The general term would simply be or -1 raised n. Good. Here's where math gets interesting. If I generated the sequence starting at 0, I will have -1, -1 raised 0, 1. When I plug in 1, I get -1. When I plug in 2, I get 1. When I plug in 3, I get -1, 1, and dot, alternating between 2. Okay. If I summed the series, would the series converge? Odd question to ask, right? One might think, well, you're adding some, taking some away. You're putting one in, taking one out. That's pretty much what I'm doing, yes? Yet at the same time, it's not going to converge. The series, as you add the stuff together, that gets into more theory, but one might think that if you add, subtract, add, subtract, add, subtract, you would end up with 0. That is not the case. You're not going to end up with 0. The series will not converge. Good. Can you think of an alternating series that is not geometric? We actually did this. The very first day when I did sequences. How about this? Do you think that would go back and forth? Yes, no, maybe? Caitlin? It is going to go back and forth. Do you think that it's going to converge? No? Grab your calculator. It is going to converge. Okay, I'm going to enter that sequence. I'll be able to see it there. Last time I had n pi of 600, I crashed that. 24. Times. Second insert 1 divided by 2 raise n close paren. And you can see it is going, well, what no flow error. We can oh, we don't want 10,000. Let's do 100 and see what happens. That is taking time. Bring 0. Okay, you can see that that is what I get. Is it becoming 0? No. If I adjust the, in other words, is it becoming exactly 0? No. I'm going to adjust the minimum and maximum values. What is the maximum value that we could get in that expression when n is equal to 0? 1/2 raised 0 is 1. Sine is bounded by 1. So I overtake 1. And I killed it. But the curve, I do want you to try. It is going to eventually get closer and closer to 0. Initially, there it will go back and forth.